to several libraries, including those of MIT, Stanford, CMU, and internationally. So the title of this talk is Minimizing the Ecological Footprint Using Machine Learning. Thank you so much for accepting our invitation, and it's all yours.
Thank you so much for the kind introduction. And so we have all been hearing about machine learning used in various aspects in this conference, right? There are quite a few applications that you would have seen presented in this conference where machine learning has been used. Even the previous talk mentioned about machine learning. So machine learning is the modern day electricity. So the same thing that electricity did 100 years ago, is machine learning is doing it now. So wherever there's a requirement for modernization, machine learning is rapidly being used. So there was a nice tutorial, I think yesterday or day before yesterday, on machine learning for social good, where some of the topics of machine learning were covered. And we saw that machine learning is all about minimizing a loss function, right? So what if the loss is ecological footprint and we use machine learning to minimize it? But it is not that simple, or at least not to my knowledge. Instead, machine learning is used to minimize the use of major contributors to the carbon footprints. So we have been hearing about the major contributors to the carbon footprint, like energy, transportation, and food, and things like that. So we use machine learning for minimizing the consumption. So what can machine learning do for us? Or what can machine learning do for sustainability? There are two parts to sustainability, right? One is conservation and the other is resilience, right? We need to do our bit to make sure things are good. The consumption is not, we are not overburdening the nature, Mother Nature. And we should also accept the fact that we are overburdening the nature. And it is obviously causing a lot of climate changes and things like that. So we should also learn to be resilient to what is happening around us. So machine learning can help in both ways. So one of the biggest contributors to carbon footprint, in my opinion, this is not told in any research paper or any book, but in my opinion, the largest contributor to to ecological footprint is uncertainty. For instance, many people would have registered for this conference, but we are not seeing all of them here. But the food would have been ordered for all of them. So that uncertainty of who is going to attend the conference caused a lot of food wastage, right? So that is adding to the carbon footprint. Another example is, suppose the room got changed for this talk and you didn't know which room it is. So there's some uncertainty. You would spend more energy finding out where to go and things like that. So uncertainty is the major, in my opinion, that's the most contributor to the ecological footprint. And machine learning reduces that uncertainty. For today's talk, it's mostly classification and regression, which are the two major aspects where machine learning really helps. And at scale, all of us can classify, say, 1 image, 2 images, 10 images, 20 images. But if it is 1 million images, we need machine learning, tools like machine learning. So classification and regression at scale is what is the real contribution of machine learning to, or most contribution to machine learning to sustainability. So the major thing is machine learning helps reduce uncertainty. And of course, we need data to power the machine learning algorithms, right? Of course, there are other aspects of machine learning which have been used in the literature, like unsupervised learning, and we also saw some NLP techniques and things like that. But the focus for this talk, this 20-minute talk, is regression and classification. And as a byproduct, we also have what is called as the importance of the contributors to classification. We'll talk about it in the next slide, next 1 or 2 slides. But the feature importance is one of the contributors, side products of our machine learning algorithms. And also pattern extraction, right? You can extract a lot of patterns from the data using machine learning algorithms. So conventionally, the way we process data, we all pretty much know about this, I think. Conventionally or traditionally, the way we process the data was looking at it as a database, right? It's a table of numbers, or text also is fine for databases. So we viewed them as a relation in set theory, right? So each row is considered a tuple, basically, in a relation, right? So that has been the traditional approach to data for a few decades. I think 2 or 3 decades, that was the predominant approach to data. And all the columns are treated equally. Though I label the last column as Y, it's still treated equally. So that has been the traditional approach. Now with machine learning, there's a new perspective. The new perspective is to view the table of numbers as a function, right? We all know that function in set theory is a special type of relation, right? You constrain the relation by adding some additional rules, it becomes a function. So what we are doing in machine learning is basically converting the data from vector space to function space. So each of the rows in the table is basically a row vector, right? You can think of it as a row vector. So we represented the data in vector space. That means each row becomes a vector. And that we are moving to function space. So we are converting the entire table into a function, which can be modeled with the function f, which depends on the x, which are the columns, other than the last column. The last column is y, and the remaining columns are x's. So we are giving a special significance to the last column. That is called the target variable, and it is expressed as a function of the remaining columns. So just a small difference in how we view data changes it all. I mean, we still have the data as a table, but just viewing it as a function instead of a relation makes all the difference. Now we can fit a curve to the data, because f is a function which can be plotted in as a on a 2-dimensional or n-dimensional plane space, right? So once we fit a curve, we are able to extrapolate, interpolate, predict, and do lots and lots of things. So we get a whole lot of power. And then we have what is called as a neural network, which is simply a combination of 2 functions. A sum of products, which is a linear component, like ax plus by is a sum of products, right? Ax is one product and by is another product. So that is one function. And the other function is a nonlinear component, like a sigmoid, S-shaped function. So using these 2, neural network is able to approximate any function, literally any function, just with a combination of these 2 components. So that is the power of deep learning. Deep learning is all about neural networks, right? So we heard in the last panel discussion as well, where deep learning was being used for natural language processing. So that's where the power is coming from. It's a universal approximator, a neural network, right? A little more detail. So how do we do classification using machine learning? So like we talked, rows are instances of entities, right? So it could be people, customers, emails, homes, or pixels for that matter, or rather images, and columns are features. So those the columns are the features of those instances, which are rows. And the last column is the classification category. So we basically use the data and the result in the last column to generate the program. The program is a model. See, it's a paradigm shift here. So we use this model to predict the behavior of a new item. So each instance, it could be a person, it could be an email, it could be a house, becomes a point with magnitude and direction in vector space. We all know vectors are basically points in space with magnitude and direction. So each instance, it could be an image, it could be a person, it could be any instance, it becomes a point in space. So those are the key ideas of machine learning. I know you had an introduction on Thursday, but I just wanted to give a different perspective to machine learning. So now coming back to our ecological footprint, what are the major contributors to ecological footprint? So this is the US government's assessment of the contributors. 25% of the ecological footprint, or the greenhouse gas emissions, which is one kind of measure for the ecological footprint consumption, is from the electric power, and 27% is transportation. So these are two major areas. So let us look at how machine learning, using the concepts that we discussed so far, can contribute to at least these two areas. First is the energy. Right? So what can machine learning do for energy? So the main goals of forecasting the solar or wind energy are to reduce reliance on polluting power plants, right? Today, power is still being generated using coal, right? It is quite surprising in spite of our knowledge of things. Coal is still being used. And then the other aspect is where and how much new renewable energy plants should be located. Where should the new ones be built? So these are two of the primary goals of energy forecasting. And this is particularly important in developing countries where the energy production is done in very non-conventional ways, or rather non-renewable ways, like diesel generators, wood burning stoves, and such things, which are really high carbon footprint. Machine learning also helps in lowering avoidable losses by predictive maintenance of the electric grids. So if there's a problem with the electric grid, it probably causes loss, energy loss, right? So preventive maintenance using machine learning helps there. And then in terms of battery, there's a lot of machine learning going on in material science. So back 100 years back, when the filament was invented, Thomas Alva Edison had to play with a lot of materials before he finalized the material for the filament, right? Electric bulb. So that can be easily done today using database methods, particularly machine learning and things like that. So techniques like that are being applied for the battery composition, right? And this table lists a few machine learning models used in literature for renewable energy applications. So here again, the main thing is to predict or forecast indicators of energy from solar and wind and so on, right? So predict the irradiance and things like that. And one thing to note from these tables is that the techniques are not too involved. In fact, if you can see, most of the techniques are traditional machine learning, if you are familiar with machine learning. very few techniques are based on deep learning techniques, artificial neural networks. Most of them are traditional machine learning, but substantial results have been achieved. The next area is transportation. So how can machine learning help transportation? I think a lot can be done here. And the first aspect is, of course, our self-driving car. So discussion on this topic cannot be complete without talking about self-driving cars, right? So self-driving cars is mainly enabled by machine learning, right? You recognize objects using machine learning, and it needs to be trained on billions of miles of data. Self-driving cars, we all know, make the transportation much, much more efficient, right? Tailgating, which is illegal if you do it manually, is legal when you use self-driving cars because of the vehicle-to-vehicle communication. The trailing car can probably coordinate, synchronize with the car at the front and probably tailgate much more closely, right? So self-driving cars is, machine learning is enabling self-driving cars, and which is a great enabler for mitigation of the carbon footprint. And there are a bunch of other applications where machine learning plays a big role. We all know how Uber and Lyft use machine learning pretty substantially for shared mobility optimization. And the other popular area of transportation where machine learning can help is bike rebalancing. So we all know, we walked through the San Jose downtown, we find bicycles parked at one location more than others, right? Some other locations are almost empty. And quite a few students who attend San Jose State University, where I teach, use these bikes because I believe PG Cares program offers them for free, right? So bike rebalancing is one area where machine learning can help. It can predict the demand and supply at various stations, and then you can rebalance it. This is particularly important in Europe because bike sharing is a popular concept there. And you can adjust the prices based on the availability of the bikes at a particular location. You can rebalance. And the other major area is in the electric vehicles space. So we all know electric vehicles will be the way to go in the future. We recently saw the White House, Joe Biden's executive order, which requires half of all the new passenger vehicles by 2030 in the United States to be powered by electricity, right? So this means there will be millions of energy storages on wheels. The aggregated storage could run into terawatt hours, right? The huge storage potential there. And so that potential can be used to balance the demand and supply of energy. So instead of just storing electricity in the car batteries, the other way to think of it is the car batteries are probably the cheapest source of storage of electricity power, right? And they are getting cheaper by the month, I think, right? With new innovations happening, the storage of car batteries is becoming very cheap. So there's a lot of potential there. So that's where this V2G comes, V2G or V2X for that matter. V2G stands for vehicle to grid. So you can actually transfer power from the electric cars to the grid to balance the demand and supply. Not only to grids, you can actually power homes and buildings and whatnot from the storage, energy storage in your cars. So there's a huge potential there, and predictions help there a lot. Machine learning is used for predictions in this space as well. And in terms of waste management, we all know if a company treats hazardous waste, or if an entity treats hazardous waste as non-hazardous, it can potentially lead to a lot of problems. And government has huge penalties when such things happen. So classification of waste is an important aspect. And machine learning is very good at it. Like I mentioned, one item, 2 items of wastage, people are good at classifying. But if it is millions of items of wastage, then you need to use machine learning. And that's where all this work that you're seeing on the slide come in. So it's basically waste prevention, reuse, recycling, and composting, which should be prioritized over landfill disposal. So that is the main goal of waste management, and machine learning can help here. So it can optimize the routing of the pickup trucks, what do you call them? The garbage collectors, right? So if the demand for, or if the generation of wastage is minimal in certain places, those places can be skipped for some weeks and things like that. So prediction helps in waste management as well. And then finally, ecological footprint prediction. There has been a lot of work in predicting the ecological footprint itself. So there's plenty of work. For instance, the first work takes data from 1996 to 2015 from Beijing, China, and applies machine learning. And the good thing is they're able to predict, or they're able to find out the key contributors. Like I mentioned, machine learning, the side product of machine learning is feature importance. Which column in the table contributes most to the last column of the table, right? So that can be determined. And so for each of these ecological footprint prediction jobs, a key contributor has been identified. For instance, in the first case, China, construction, urbanization has been a major contributor there. In the second case, in the second study, again in China, but a place closer to it, Tianjin, the contributors are again urbanization, population, and industrial infrastructure. Whereas in the case of 41 other countries, which is the third work listed on this slide, the major contributor is fossil fuels. So we can identify key contributors and take corrective actions. So I'm kind of running out of time. So for more details, this is a chapter that one of my students and I authored together in my recently published book. So you can refer to that. But a more significant treatise is a 112-page document paper produced by researchers from all these top institutions, including Andrew Ng and Yoshua Bengio, who are noted two noted names in AI/ML space. So they did a lot of study of climate change and using machine learning. I mean, how machine learning can be used to tackle climate change. So I invite you to look at that paper. And then a brief note on future directions. So like I mentioned, artificial neural networks are universal function approximators. You can approximate any kind of function. So an artificial neural network looks something like this. There are a lot of hidden layers. So there is an input layer at the left, and then there are hidden layers. So the new approach treats the entire hidden layer as a function. So there's a little bit of math involved, but essentially what all this means, I mean, it's a simple concept. I can explain it, but it might take a few minutes. This is a very simple concept. So the thick line is the function fx. And what are those small arrows? They are basically gradients, right? If you know a little bit of math, if you remember math. So those are all gradients. So artificial neural networks basically compute those gradients. They compute the curve by using those gradients. The latest approach is to treat them in a continuous fashion instead of as the gradients, small, very tiny gradients constituting the curve. We are going to treat it as a continuous curve. So that makes a whole lot of difference. Why does it make a whole lot of difference? Because once you have the curve, you will be able to extrapolate, interpolate, and things like that. Even if the signal is choppy, even if the input is choppy, you can still extrapolate. So the advantages are that, in the last panel discussion, they talked about NLP techniques, right? So there's a famous NLP model called GPT-3, which is the trend now. So that uses billions of parameters. That means these connections, interconnections are billions. So with this kind of approach, all those billions of parameters are gone. The hidden layers are all gone. So no need for billions of parameters, and then less computational needs. And then we already talked about extrapolation and things like that. And the other aspect that's quite interesting is called the Legendre memory unit. This again is a mathematical concept. It's a function space. Legendre polynomials define a function space. The advantage of this is that it can track the sequence up to more than 100,000 time steps. A typical neural network, which was talked in the last panel discussion, like there was an LSTM and things like that, which were shown. They can go up to maybe 512 or at most 2048 time steps. But this can go more than 100,000 time steps. So these are very important for climate and the sustainability kind of data, because first thing is it is not continuous, it's not, it's choppy. And the second thing is the sequences are too long to be remembered by LSTM. So I'll not go into these details. You can check. There's also related to this. Okay, so related to this, I don't know why this is not okay. Related to this is also what is called as liquid neural networks, liquid AI, which is getting popular. It has all the advantages of neural ODEs that we talked earlier, and there are some additional advantages as well. So that concludes my presentation, and you please feel free to contact me anytime if you have any comments, feedback, but we still have some time for questions. There's a question. Oh, sorry.
Really wonderful, inspiring, so there's a lot of discussion these days about creating and regeneration. It's not just about conservation, where we're coming up with artificial ways of have you seen any of these tools or
So you mean creating new sources? Is that what you mean?
No. So in the sustainability sector, there's a lot of discussion about biomimicry, recreating biological or artificial technologies that mimic the environment, and regeneration works out not just using less, but actually regenerating giving back more. So it's still pretty recent, but it seems to me that with the methodology we were talking about, we can not only benchmark and mimic what's happening in the real world, but actually model what could. Because right now the difficulty is finding funding that will rely on the data that says, yes, this biomimicry regenerative technology is actually good for this. Does that make sense?
Yeah, I think I got the question. So the question is mimicking the biological process of generation, whether machine learning can help in that process. Yeah, definitely. I haven't specifically studied that kind of a thing in the literature, but I can easily see how it can really help. So of particular interest are generative models in deep learning, where data can be generated. So the data can be generated to model real world as well, or biological generation process itself. So it's all about data, coming up with the data for us to do the analysis and things like that. And generative models really help in that aspect. Does that answer? Thanks. Any other questions? Yes.
I want to go back to one of the first slides that you showed in terms of classification. And you showed an electricity sector, civil diagram, and a transportation sector. If we go to electric vehicle, there you go, electric power and transportation. What happens to this diagram if we go to electric vehicles? Does that, we're still using electric power, so does that increase or decrease the percentage in transportation in electric power?
That's a very good question, actually. So if I had to guess, I mean, the whole purpose of using electric vehicles is to reduce both of those, right? Both the electric power consumption and transportation. But yeah, I know there's a lot of debate about it, because one of the major challenges, even if we go nuclear, one of the major challenges is the input must be less than the output. So we need energy to, even for nuclear fusion, we need energy. So that energy most of the times is more than what it is able to produce. So it's a challenge which is being addressed through material science and things like that. And machine learning is certainly helping there. But yeah, the goal is essentially to lower both the areas, the ecological footprint for both electric power and transportation. But yeah, it's a very challenging road ahead. That can be easily said. Thanks for the question. Any other questions?
Great talk. Interesting stuff. So in the sustainability, question, there's two aspects of it. One is, to generate electricity or generate power in a renewable fashion. That's one of it. The other one is to improve efficiency. So it seems like you have addressed the generation part. Should we also apply the same techniques to improve efficiency in our economy to reduce consumption?
Efficiency in the power plants or efficiency in the economy?
In general, the energy consumption.
So broad, if I had to answer it very broadly, machine learning is basically an optimization technique. We essentially optimize. So wherever optimization is there, there is a scope for machine learning. So yeah, definitely there are multiple possibilities there. Any other questions?
All right, thank you so much. We're running out of time. So we have about 15 minutes break, and then we will have technical sessions in 1301, 2301, 2302, 3301, and 3302. Okay. Thank you so much. Here's the certificate, and it's a small gift for you.
Oh, thank you.
Okay. Yeah. Yes. Thanks.
Thanks.
And by the way, the banquet will start at 6 p.m. It's going to be in Locatelli. If you don't know how to walk to Locatelli building, please ask the registration. Okay. We have a map. And then we can speak about what.
Yeah,
Thank you, Vishnu.
sure. Thanks.